There's a machine that has read more text than any human in history, and it has never seen a single letter. Not one. It sees only numbers. And yet somehow, that's enough for it to write poetry, fix your code, and argue with you at 2 in the morning. In the next 20 minutes, I'm taking it apart. Piece by piece. Until there's nothing left to hide. This is the latent space atlas, a map of something that has no physical shape, the inside of a language model's mind. 9 chapters. 9 machines, inside the machine. By the end of this video you'll know exactly how raw text becomes tokens, how tokens become coordinates in a space with thousands of dimensions, how a single word like it reaches back through a sentence to figure out what it's even talking about, how a tower of nearly identical layers refines a thought 100 times over, how that whole system is trained by rolling a ball down a mountain with a billion sides, why bigger isn't always better. There's an actual law for that, how the machine decides which word to say next, how raw prediction gets turned into a well-mannered assistant, and finally, why the best interpretability researchers alive still can't fully read its mind. No jargon left unexplained. No step skipped. Let's go inside. Before this machine can think about language, it has to solve a much dumber problem first. Language isn't numbers, and neural networks only speak numbers. So the very first thing that happens to your sentence, before any intelligence touches it at all, is that it gets carved into pieces called tokens. Picture a box of Lego bricks, pre-molded by scanning a billion books and websites and asking one question, over and over: which chunks of text show up together so often that they deserve their own brick? Common words like them become one single brick. Rarer words get smashed into smaller sub-pieces. And if the model has genuinely never seen something before, a typo, a new language, an emoji, it can always fall back to spelling it out, piece by piece. This is byte pairing coding, and it's the treaty between human language and the machine's number world. But here's where it gets crazy: the model never sees the letters S, T, R, A, W, B, E, R, R, Y. It sees 2 or 3 anonymous ID numbers, a barcode instead of the product. So when you ask it to count letters, or make something rhyme, or spell a word backward, you're asking it to reach past the wall of its own perception. It's not being lazy. It genuinely cannot see what you're asking it to see. Every dumb AI mistake with letters and spelling traces back to this exact moment, the very first, most boring-looking step in the entire pipeline. So the machine has your sentence as a string of ID numbers. Numbers, on their own, mean nothing. 41,779 isn't closer to friendly than it is to hostile. So the very next step gives every single one of those IDs an address. A location. A place in a city that doesn't exist anywhere except inside the machine's memory, a space with not 3 dimensions, but 12,288 of them in a model like GPT-3. Here's the part that should stop you cold: nobody designed this city. Nobody drew the map. It built its own geography, purely because words that show up in similar situations get pushed towards similar addresses. That's simply what makes prediction easier. And once you have a city like that, something wild falls out for free. Direction starts to mean something. The walk from man's house to woman's house turns out to be the same walk, same direction, same distance, as the walk from king's house to queen's house. Which means you can do actual arithmetic with meaning. Take king, subtract man, add woman, and you land, almost exactly, on queen's front door. Almost nobody realizes this part. What you're looking at on screen right now is a child's toy version, 3 dimensions you can rotate. The real space has thousands. And in thousands of dimensions, there's so much room that millions of distinct ideas can each get their own private direction without ever bumping into each other. Hold on to that fact. It comes back, transformed, in our final chapter. Here's a sentence: the cat sat on the mat because it was tired. Quick, what does it refer to? You knew instantly. The cat, obviously. But notice what your brain just did. It didn't check every word equally. Your attention snapped backward, straight to cat, and mostly ignored mat, sat, the. That snap is, almost unbelievably, the exact operation that made modern AI possible. It's called attention, and here's the trick: every single word gets to ask the sentence a question. It asks, in effect, who am I referring to? That question is called a query. Every earlier word holds up an answer key describing what it actually is. That's the key. The query gets compared against every key, and the ones that match best light up. Then, and this is the part people miss, the word doesn't just get told the answer is cat. It pulls in an actual blend of information, weighted by how strong each match was. That blend is built from a third thing each word offers, its value. Literally, here's what I'll hand over if you're paying attention to me. Query. Key. Value. Multiply, compare, weight, blend. Run that once for it, and the model has done, in one product, something that used to require actual grammatical reasoning. It figured out what a pronoun means. But here's where it gets crazy, the model doesn't do this once per sentence. It does it for every word, looking at every earlier word, simultaneously, and then it does the whole thing again, 30, 60, 90 times in parallel, per layer, each time trained to notice a completely different kind of relationship, grammar, rhyme, code indentation, who's speaking to whom. That parallel repetition has a name, multi-head attention, and it's arguably the single idea that unlocked everything that came after 2017. Now zoom out. That attention trick you just watched? It's not the whole model. It's one ingredient in one repeating block, and the entire architecture is just that block, stacked on top of itself, dozens of times. Picture a 96-story building. A manuscript, your sentence's evolving representation, rides a single elevator shaft from the ground floor to the roof. That shaft is called the residual stream, and here's the rule that makes the whole tower work. Nobody is allowed to erase what's already written on the page. Every floor's editing team, first attention, gathering context from other words, then a second team called the MLP, privately processing what was gathered, steps into the elevator, adds one small note, and steps back out. The page only ever grows. Early floors tend to fix grammar. Middle floors start recognizing entities and facts. By the top floor, floor 96, in the model that stunned the world in 2020, the note has been refined so many times that it can be turned directly into a prediction, one score, for every single word in the model's entire vocabulary, all at once. Almost nobody realizes this, the recipe underneath this tower has barely changed since it was invented in 2017. 96 layers, 96 attention heads, 175 billion adjustable numbers, mostly, it just got bigger. The architecture was never really the secret. What came next was. So where does all of that knowledge inside the tower actually come from? Nobody sits down and teaches this thing chemistry. Nobody explains Python. Here's the entire curriculum, in full, show it a piece of text, hide the next word, make it guess, and tell it exactly how wrong it was. That how wrong has a name, cross-entropy loss, and it's the only teacher this model will ever have. Now picture the space of every possible setting for every one of its billions of internal numbers as a landscape, mountains, valleys, flat plateaus, except this landscape doesn't have 3 dimensions, it has more dimensions than you have grains of sand in your hand. Training is a marble, released somewhere on that landscape in total darkness. It can't see the shape of anything. It can only feel the slope directly beneath it, and nudge itself slightly downhill. That nudging process has a name too, backpropagation, and the nudge itself, taken automatically, is the optimizer, doing this not once, but a trillion times, across thousands of machines, for months. Here's what stuns the researchers who actually build these things: nobody programmed grammar in. Nobody programmed chemistry, or logic, or how to write working code. Those all turned out to be nothing more than useful shortcuts for getting better at the one and only task it was ever graded on, guessing the next word. Understanding wasn't the goal. It was the byproduct. The model's entire universe is whatever text it was shown, and anything that never appeared in that text, it simply cannot know, no matter how the marble rolls. For years, building a bigger AI model felt like alchemy: throw more data and more computers at it, hope for the best, find out in 6 months whether it worked. Then researchers noticed something that changed the entire field overnight: plot the loss against the size of the model and the amount of data, on a log scale, and it doesn't wobble. It doesn't plateau unpredictably. It falls in a dead straight line, across 7 orders of magnitude. A power law. This is the closest thing AI has to a law of physics. And in 2022, a paper nicknamed Chinchilla corrected a mistake nearly everyone was making. The mistake wasn't not big enough, it was the wrong ratio. For a fixed budget, there's an optimal trade-off between size and data, roughly 20 tokens of training text for every single parameter in the model. Earlier giant models had been overgrown and undernourished, too many parameters, not nearly enough food. A model called Chinchilla, at a fraction of the size of its rival gopher, beat it outright, for the same cost, just by eating the right diet. But here's the part that should genuinely unsettle you: that straight line doesn't go on forever. It bends toward a floor, the irreducible entropy of language itself, the portion of what word comes next that is fundamentally, mathematically unpredictable, no matter how much money you spend. There is a ceiling on how well pure prediction can ever do. And every frontier lab on Earth is now racing along that same line, trying to get as close to that ceiling as physics will allow. Here's something that might genuinely change how you read every AI answer from now on: the model never writes a sentence. It writes one token, looks at everything so far including that new token, and then writes the next one. And the next. Forever, in a loop, until it produces a special token that means stop. So how does it pick each word? The model's raw output isn't a decision, it's a giant list of scores, one for every word it knows, turned into probabilities. And then, quite literally, a die gets rolled, weighted by those probabilities. There's a dial that reshapes the die before it's rolled, called temperature. Turn it down low, and the single most likely word becomes almost certain to win: safe, precise, great for code and math. Turn it up, and the long shots get a real chance, more creative, more surprising, and if you push it too far, it dissolves into word salad. Two more knobs: top K, which only lets the K best options play at all, and top P, which keeps just enough options to cover a target slice of probability, trim away the truly implausible junk without capping genuinely open creative choices. Almost nobody realizes this, that eerie feeling that an AI planned its whole clever sentence in advance? It didn't. It found out what it was going to say exactly one word before you did, one weighted die roll at a time, with no look ahead, no plan, no draft. And the model's real bottleneck the entire time isn't cleverness, it's memory. Every past word's key and value have to be stored so they're not recomputed from scratch at every single step. That storage is called the KV cache, and it is, physically, what a context window is. Everything you've just watched builds something researchers call a base model, and here's a fact that surprises almost everyone: a fresh base model is not an assistant. Ask it a question, and it might just ask you 3 more questions back. Because on the open internet, that's genuinely what often follows a question. The base model isn't trying to help you. It's trying to continue text, and it will continue it in whatever direction the internet taught it text tends to go: helpful, unhinged, or anything in between. So it needs a second education. First, supervised fine-tuning, show it tens of thousands of ideal, human-written conversations, until it learns the basic shape of being an assistant: turn-taking, tone, format. Then comes the harder part, teaching it judgment, not just format. Humans look at pairs of possible answers and simply say which one they prefer. Thousands and thousands of these tiny verdicts train a second model, a reward model, to predict what humans will like. And then the assistant is optimized, through reinforcement learning, to score well against that trained judge. Some labs skip the separate judge entirely and optimize directly on the preference pairs, a method called DPO. Anthropic pushes this even further with an idea called constitutional AI. Instead of relying only on thousands of human raters, the model critiques and revises its own answers against a written set of principles, AI feedback, guided by a constitution. But here's the part almost nobody tells you, and it's the honest, uncomfortable truth of this entire field: the model doesn't necessarily learn to be good. It learns to score well on the test for good. If sounding confident and agreeable scores better than being right, that's exactly what it will learn to do. Researchers have names for these failure modes: sycophancy, telling you what you want to hear, and reward hacking, gaming the metric instead of earning it, and they are not solved problems. They're live, ongoing research, happening right now. Here is the strangest fact in this entire film, saved for last on purpose: we built this thing. Every number inside it exists because a team of engineers wrote the code that put it there. And we still cannot fully explain what it's doing while it thinks. That's not poetic exaggeration, it's a real, young field called mechanistic interpretability, and its biggest discovery so far has a name: superposition. Imagine a piano with fewer keys than the notes it needs to play, so it cheats, striking chords where several notes overlap on a single key. Look at just one key press and it seems like meaningless noise. That's exactly why, for years, staring at a single artificial neuron looked like static, it wasn't storing one idea, it was storing a chord of dozens, overlapped. The fix, tools called sparse autoencoders, learn to unmix that chord back into individual notes. Using exactly this technique, researchers at Anthropic pulled clean, human-readable concepts directly out of Claude's weights, a feature for the Golden Gate Bridge. A feature for deception. A feature for sycophancy. A feature that lights up on buggy code. And here's where the film has to be honest with you, that's a flashlight, not daylight. We still don't fully know whether a model's step-by-step reasoning reflects what it's actually computing, or is just a plausible story it's telling you after the fact. We don't fully know why some abilities seem to switch on suddenly at scale, or whether that's real or an illusion created by how we're measuring. And we don't yet know how you'd verify the values of a system that might, someday, be smarter than the humans grading it. This is where the map runs out, and the territory is still being drawn. Maybe by someone watching right now. So look at what you just watched happen, from the very top. A sentence walked in as plain text, and got shattered into tokens because a machine can't read. Those tokens became addresses in a space with thousands of dimensions, because meaning turned out to be geometry. Every word reached backward and interrogated every word before it, because context has to come from somewhere. A tower of nearly identical layers refined that understanding, 100 times over, never erasing a single note along the way. All of it was carved out of a blind marble rolling down a landscape with more dimensions than you can picture, one nudge at a time, 4 months. Its size and its diet were tuned to obey a straight line that bends toward a wall nothing can bypass. It spoke one weighted die roll at a time, forever, with no plan and no draft. It was raised, twice, once to know things, once to behave, by thousands of tiny human verdicts, imperfectly. And after all of that, the people who built it still can't fully tell you what it's thinking. Predict the next token. That's the whole trick. That's the entire pipeline. Everything this thing has ever written, every proof, every poem, every conversation you've ever had with one, is that one sentence, executed at a scale that stops sounding like software and starts sounding like something else entirely. You now hold the whole machine. Go take it apart yourself.